Okay, here we go. So last time we were talking about how to visualize partial derivatives, specifically second partials, right? So second partials, we have an existing geometric interpretation of first partials, and that's about slopes of tangent lines and stuff like that. Second partials are different. Now the good news is the unmixed second partials, like fxx and fyy, where you're taking the partial with respect to the same variable, right, both times. You're just setting one variable to be a constant and then literally taking the second derivative, and so concavity kind of holds, right? It's still concavity, just like it is in single variable calculus, per this picture here. Again, I made the note last time that even though this is a kind of a familiar idea, right, concavity, we see now that there is a possibility in multivariable that does not exist in single variable, in that there are two different directions in which you can talk about second partials, and they don't have to agree, right? So Pringles exist, and so you can have a situation where fxx is negative, fyy is positive, as we saw last time. So, a little bit weird. Okay, now here's where it gets tricky. And that is, how are we going to deal with mixed partials? How am I going to understand the x partial of the y partial? This is going to require taking a very delicate, very particular, specific point of view to make sense out of it. First thing I'm going to do is talk about how will we understand the y partial itself. I'm going to say, sure, let's suppose we're looking at the graph of f. The y partial is, well, it's the slope of the tangent line in the y direction, right? Old news. So I'm going to draw a picture of that here. Now, one thing you're going to notice conspicuously absent from this picture is that I didn't draw the graph itself. I didn't draw that surface. But I feel like some of what we need to see about the graph itself, you can kind of see from these tangent lines that I drew. So specifically here, going in the y direction, right? If I were to look up onto the graph as I move in the y direction down here in the domain, let's suppose that the tangent line were, like that, let's say. Now, so this being the tangent line directly above that green arrow. Okay. So in this particular, at this point, right, for the function in question, as I have it drawn here, the y partial at that point is like -2, something like that. Just, eyeballing from the picture. Okay, now I'm going to do the same thing in various other places, here, or here, or here, or here, right? And I draw these tangent. Each one of these is at a different point, still all going in the y direction, but at a different point, each of them. And so I get different tangent lines. And let's suppose that these tangent lines look like what I have drawn here. I'm sorry, my left hand is not as coordinated as my right, so well, we get what we get. So, that being said, now we have to figure out, from what we're looking at here, how are we going to interpret the x partial? And here's where it gets really tricky. We cannot interpret this x partial here as indicating a slope. Because if you want to interpret a partial as a slope, you have to be looking at a graph. We are looking at the x partial of the y partial of f, not f. Right? So I'm looking at the graph of f. I don't have a graph of the y partial of f. Therefore, I cannot make a graph interpretation of the x partial. Does that make sense to everybody? We're looking at the wrong picture. The x partial, the thing we're taking the x partial of, is something that we're not looking at the graph of. So I'm going to take a different interpretation of that x partial. Reminder, another way to think about a partial derivative is it says, how fast is that thing changing as you move in the x direction, right? And so that's why I drew the y partials at these various locations, Because now I can say, okay, now look, as I move in the x direction, right, this little blue line down here in the domain sort of represents me moving in the x direction, and as I move in the y direction, as I move in the x direction, I want to know how are the y partials changing, right? So you look at the picture here. Okay, let's just kind of follow this blue line. When I'm back here, the y partial looks like about -2. As I move forward in the x direction, now the y partial appears to be about -1. As I continue to move forward, about -0.5, about 0. Now slightly positive, maybe +0.5, something like that. Notice as I go in the x direction here, my y partials are increasing. So interpreting the x partial is as how fast is that thing that I'm taking the x partial of, how fast is it increasing, and seeing that, well, it's increasing at a positive rate here. What we're looking at a picture of must be where this mixed partial, the x partial of the y partial, is positive. Does that make sense to everybody? So it's a delicate little geometric argument. You got to interpret. We have two different partials, and we're interpreting them differently in the same context. It's kind of weird. How we doing? Oh yeah, question.
So what are the top lines?
Yeah, so this is, I mean, look, drawing three-dimensionally is hard, right? So imagine that there's some surface here. For each one of these green lines representing me going in the y direction, these are the tangent lines on the mystery surface as I'm going in the y direction above each one of these points. Does that make sense? Yeah. So now, so what does this look like? I mean, if we wanted to geometrically describe what am I seeing, right? So we can have a geometric interpretation of mixed second partials, kind of like, well, you know, the x partial, the slope of a tangent line in the x direction. Second partials, unmixed second partials or concavity in that direction. How would I describe this geometrically? And my best answer is to say that it's a twist, right? And I have to appeal to your ability to visualize in 3 dimensions here, but it's like something kind of like this is happening. Does that make sense? It's kind of a weird thing to think about. There is no 2-dimension. There is no single variable version of this, right? Don't look to your Calc 1 experience for, oh yeah, it's just like such and such from Calc 1. Nope, not at all. Totally brand new concept. Mixed second partials look like a twisting of the graph. And they use the word torsion, but that's a big word, small meaning. Yeah?
So you said that as you go in the x direction, then the y partials are increasing?
Mm-hmm. Yep.
Like how?
Because, yeah, that's right. Let me walk through it again. So we've agreed that at this point here, the y partial being the slope of that line, at this point the y partial is about -2, and then here it's about -1, and then here it's about -0.5, and then as I move in the x direction, those y partials are getting larger and larger.
Okay.
Is that cool? They're increasing, I guess.
Yeah, okay.
Yeah. And by the way, I made them negative instead of positive just because it's easier to draw that way. Purely artistic laziness on my, artistic deference, right? I wanted it to be easy to draw and easy to visualize. So that's my best shot at it there. Okay. All right. So that's partials. We're going to move on now to section 3.1. This is a jumping out of order. Basically, section 3.1 introduces a point of view that I'm going to make use of in a few minutes when we get into section 2.5. And here's the big idea. Y'all recall, of course, this idea of a parametric curve. Remember, a parametric curve gives you position. The output is position, right? As a function of, well, a single parameter, but most of the time, for kind of geometric and physical convenience, we think of that as being time, right? So position is a function of time, typically. All right, so that being the case, here's what the derivative matrix looks like. And this is easily confirmed because there's only one input variable, therefore only one column. Remember, columns correspond to input variables. Okay, so that's weird. Now here's another thing we could write down, just hypothetically. If I were to forget about all this multivariable calculus we've done and just ask, let's go back to Calc 1, definition of a derivative. This is what we would write down to be the derivative of this parametric curve, this position as a function of time. And notice it's fine. It works no problem. I need to take a difference of two outputs. Cool. The outputs are vectors. You could totally take the difference. Not a problem. Let's see. I need to divide by the difference of the inputs. So t plus h divided by t, that's just h, right? No sweat. So you can totally write this down, and there you go. That's the derivative of a parametric curve. And notice, they're kind of the same, right? The derivative matrix and the sort of single variable point of view happen to be, about the same deal. You just take the time derivative. Everything's a function of one variable time. Just take the derivative with respect to time, one coordinate at a time. Okay. All right. What's nice about this is it allows us to make an interpretation based off previous experience. So specifically, if I look at this expression and ask what does that look like geometrically, the numerator up here is displacement. I was here. After a certain amount of time, I became here. That numerator is just the difference, and the difference says how much did, in amount of time, h, how much did I move? What was literally my change in output position? So displacement, and then notice my denominator is the elapsed time. So this expression here is pretty literally displacement per unit time. And you can see from the picture that those displacements in the limit, as h approaches 0, those displacements become tangent to the curve. And displacement per unit time is an old concept. It's velocity. Okay. So we get this old familiar idea. This thing, the derivative matrix, aka the single variable derivative of this parametric curve, is just a tangent line or tangent vector known as the velocity vector. So very handy interpretation for parametric curves, and I emphasize this only works for parametric curves. Derivative is the velocity vector. Is that cool? All right. Okay. Likewise, the second derivative is acceleration, another familiar old physics concept. Okay, so that's going to allow us to answer this example question here. There is a parametric curve that we're interested in, but we are not given the parametric curve. We're given the velocity. And given the velocity, how do I conclude? Well, first let's ask what's the acceleration, but then how am I going to sort of go backwards from the velocity, figure out what is the actual parametric curve itself? There's, like I say, two parts to this question. The first part, acceleration. Well, acceleration is just the derivative of the velocity that we were given. So that's an easy calculation. Flashbacks to single variable calculus, taking derivatives of functions. Okay. Where it gets interesting is going backwards to figure out what is position. So keep in mind, we were given velocity, we want position. Okay, well, we know velocity is the derivative of position. That means, just kind of changing the grammar around a little bit, that position is the antiderivative of velocity. How do you feel about that? Is that cool? maybe this might ring some bells. It's kind of analogous to some single variable questions you saw back whenever that was, a long time ago. Yeah, no problem. We have the velocity given. We can compute the antiderivatives one coordinate at a time. Antiderivatives, a matter of kind of doing it, right? But I should note, don't forget, Calc 1 and Calc 2 are all in the prerequisite trail of this class, and I'm going to assume that you are proficient with all the Calc 1 and Calc 2 stuff. So I realistically will not be doing any sort of obscure antiderivatives, right? Inverse hyperbolic trig functions. Don't worry about that. I'm not going to do that to you, right? But I do expect that you're good to go on all of the kind of the standard stuff. Polynomials, trig functions, combinations of trig functions. There's various little tricks that you can pull, right, to do antiderivatives of those. Integration by parts and substitutions are the two big sort of like, next level kind of techniques. And it's one thing to know those, and it's another thing to be good at them, right? So make sure that you're good at them and proficient and quick and reliable and all that kind of stuff. Okay. All right. So no problem. Well, okay, one problem. When you do antiderivatives, you get a constant in each coordinate, some unknown constant that has to be worked out. And if you have one in each coordinate, that means altogether you have a constant vector. Is everybody okay? Okay, so what we're going to do from here, and again, I imagine this is probably familiar, we're going to take this equation and we're going to plug in t equals 0. So we're going to plug that in to the position. We're going to plug it in to this function here, right? The position over here, x at t equals 0, we're given. That was my initial value, right? So that becomes 5, 6. This x here becomes 5, 6. Plug in t equals 0 into here, some arithmetic ensues, and anyway, the punchline is that green equation turns into this, and of course it's super simple then to solve for c. Everybody happy? Yep.
Did you just pick t equals 0 arbitrarily, or is there?
I picked t equals 0 strategically, as follows. I know that I can plug in any value of t into here, right? But I also know that in order to be able to solve for c, I'm going to also need to know what this is. And so I'm going to need to know the actual value for position at some time. So I'm going to choose whatever time it is at which I know the position. It happened to be that I was given position for t equals 0 here.
Okay.
But if you were given position at t equals 17, then you would plug in t equals 17 because that's a foot in the door. Is that everybody happy with that? Okay. Cool. All right. Now, while I'm here, I do want to comment one thing about this. A lot of people mistakenly think that the what they call the integration constant is always equal to the initial value. A lot of people think that. This is absolutely not true. I mean, case in point, right? It's clearly not true. There's two things wrong with this. One is, there is the little matter of it not being true, right? That's pretty easy to persuade students that that's a bad thing, right? But here's worse than that. It is a non sequitur, right? And keep in mind, the focus in this class isn't about answers. The focus in this class is about reasoning, right? Y'all heard me talk at great length about that. I'll stay off my soapbox, right? But that is the focus of the class, the reasoning, and the suggestion that integration constants are always equal to initial values is just absolutely false reasoning. And so that it gives you the wrong answer isn't the point, because sometimes it does. Sometimes you get lucky, right? Stop clock is right twice a day, right? So if you should happen to get lucky, it's still invalid reasoning. And again, the reasoning is what we're looking for. Does that make sense? I hope this is a really important point, but I hope that makes sense. So I need to see in a situation like this that you understand the mathematically reasonable, the process that allows you to actually conclude that value. And even if it happens to be correct, a baseless assertion that the integration constant is just the number you were given, again, even if the arithmetic works out that way, invalid reasoning, and the fact that it gives you the right answer is irrelevant. So, anyway, keep that in mind. All right. Okay. Real quick reference to some stuff that y'all are not responsible for. Remember, you're not responsible for the Kepler stuff that's in the sort of the last 2/3 or so of this section. So that's noted on the content syllabus, of course. I hope y'all are keeping a close eye on the content syllabus. And so as you read the book, make sure you don't spend a bunch of time worrying about stuff that you don't really have to, not responsible for. That said, I do want to pick out, in particular, Proposition 1.4. So you are responsible for this right here, these two equations, sort of product rules of sorts, of taking derivatives of vector valued functions. So make sure that you're comfortable with these. Everything else in the Kepler sections, you're not responsible for. Okay. All right. Moving along. Y'all remember single variable calculus. Y'all remember the single variable chain rule. I'm going to develop the single variable chain rule here. I'm going to do so in a particular way, not because I don't think you know it, right? I know you know the chain rule, but because this is going to serve as a sort of the starting point of an analogy. I do this a lot in this class. I've done it at least a couple of times, I think, so far, but I'm going to do it quite a bit more going forward. We're going to look at how did stuff work out in single variable, particularly from a particular point of view, so that I can use that to extend to the multivariable context, and then we'll make it from that point of view, analogous point of view in multivariable. So here it comes. How do we think about a derivative? Among many other choices, a derivative is a thing that you multiply by input velocities to get output velocities. Hope that is a familiar point of view. Everybody remember that? You may recall one of the earlier in this chapter, first thing I said about derivatives was derivatives are always relationships between input changes and output changes, right? And so that's what's going on here. We have an input velocity that is a rate of change. We have an output velocity that's a rate of change. So I'm thinking of the green and the blue here as being input change and output change. The derivative relates them. If you want to feel more comfortable about why this equation is true, notice you could rewrite x prime as dx dt and y prime as dy dt, and then in fact this, what I would like to think of as just being an interpretation of derivatives, you could view instead as being sort of the single variable chain rule, right? This is the point of view on it. All right, so derivatives are factors that you multiply by input velocity to get output velocity. And I'm going to say that again one more time just for the purpose of emphasizing derivatives are factors. They're multiplicative factors. Okay, now with that in mind, let's look at this scenario. Here I have a, let's see here, I have a single variable function. Y is a function of x. And then I have another single variable function where z is a function of y. And notice then that y the output from F and also the input to G, and so we can talk about composing these functions. And when you're composing, then the original input, let's see here, I'll do it like that. There we go. The original input turns into the eventual output. Right? You sort of, leapfrog over the y-axis. Is that cool? Everybody on board? Composing functions, right? Okay, so each one of these three functions, you can interpret the derivative as a factor. And so I've done that in three different places here. There, and there. The derivative of each one of these three functions is what you multiply by input velocity to get output velocity, whatever. And then you can relate these equations to each other. You can, as I wrote here in the notes, you can basically plug 1 into 2 and then compare to 3. And if you want to do that algebraically, feel free. I'm going to take I think a more intuitively satisfying take here, which is that, look, when you look at the derivative of f, and that's relating x prime to y prime, what you're really doing is you're multiplying by a factor. Again, that's what derivatives do. Derivatives, think of them as being multiplicative factors. So multiplying by f prime, and then subsequently multiplying by g prime, grand total, what have I done? If you multiply by one number and then multiply by another number, well, grand total, you have multiplied by the product. Right? And so the derivative of the composition, dz dx, it's the result of having first multiplied by dy dx and then having multiplied by dz dy. So therefore, the composition is the product of the individual derivatives. What do you think? Does that seem reasonable? Single variable calculus. So again, I hope a lot of this is familiar. Okay. All right. So again, old news. Oh, while we're here, I do like to point out that there is a pithy little sort of rolls off the tongue point of view here. Differentiation turns compositions into products. If you have a composition of functions like we do in this picture, composition of functions, when you want to talk derivatives, that composition turns into a product of the individual derivatives of your starting functions. So differentiation turns compositions into products. All right, old news, single variable calculus. Why are we reviewing single variable calculus? Again, for the analogy. We are now well poised to say, hey, let's just do the same thing, exact same thing, just now in a multivariable context. And that's exactly what we're going to do here. First of all, a derivative is a multiplicative factor. Now this time it's a matrix, but it remains. It's a multiplicative factor. It's what you multiply by x prime to get y prime. So it's a factor, just like in single variable. Yeah, I mean they're different objects. Again, the velocities that I'm multiplying by are now vectors instead of scalars. And the factor that I'm multiplying is a matrix instead of a scalar, but whatever. It's still a multiplicative factor. Okay. All right, I can apply this idea to any of the three functions involved in a composition. And here we go. Here are three functions involved in a composition. There's the first function that turns the x variables into the y variables. And then there is the second function that turns the y variables into the z variables. And then there is the composition that says, okay, yeah, all together we turn the x variables into the z variables. So you can write that down for each of these three functions, in particular that the derivative matrix this time is a factor that relates the velocities. It's a factor you multiply by input velocity to get output velocity. And again, just like we did on the previous page, you can plug 1 into 2 and compare to 3 if you want to get all algebraic about it. But it's much easier to just think of it as, look, this process here of turning that vector into that vector comes by multiplying by that matrix. And this process right here of turning that vector into that vector comes from multiplying then by this matrix. So altogether, what have we done? Well, in order to turn x prime into z prime altogether, well, I first multiplied by the df matrix, and I subsequently multiplied by the dg matrix. And so altogether, the derivative of the composition is the product of the individual matrices. All right, is that cool? Is everybody happy with that? Yeah. One more time, I'm sorry.
In the pink box.
The little circle right here?
Yeah.
The little circle is just a convenient shorthand notation that represents composition. So G compose F is how we read this, and it's this purple function that takes X variables as its inputs and then kind of plugs into both functions, consecutively to get the Z variables as its outputs. Yeah. Is that okay? Yes.
Where did the x prime go?
Where did what now?
The x prime go is the...
Oh, well, I'm just making the observation that if you look at this equation right here, this product, dg times df is what you multiply by x prime to get z prime. And now I'm comparing to equation 3 up here that says the derivative of the composition is what you multiply by x prime to get z prime. So the derivative of the composition and this product of individual derivatives, both are things that you do to multiply to turn x prime into z prime. And so therefore they must be the same. They do the same things, therefore they must be the same thing. Is everybody happy with that? Yeah.
So just to clarify, when you're taking the composition of a function and then you do the derivative, you're taking the way it's like the train rules, you're taking the derivative outside with the input value, and then you're taking the derivative of the inside.
I mean that's the conclusion that we end up with, but I mean the way I got here, so I wasn't really citing. I mean what you just described as sort of a procedural point of view on the single variable chain rule. I'm just saying we get to conclude that because you can look and see what each step in the process is, right? The process of turning x prime into y prime is involved by it. That's done by taking the derivative matrix of f, evaluated at the point where you're at, which is a. So that's this. Now, secondly, the process of turning y prime into z prime. Well, that's done by the derivative of g evaluated at this point. F of A, which is this. Yeah. So this is you might say an analogous argument that gets us to the same conclusion. Is that cool? Yeah. All right. Okay. So now there's a bunch of different points of view on how to think about the multivariable chain rule. This one's my favorite. I like to think of multivariable functions not really as being functions with multiple coordinate inputs, but think of multivariable functions as functions with vector inputs, right? And then think about, well, what do derivatives do to those vectors? And once you have that point of view, well, then unavoidably derivatives are matrices. And so the chain rule, from the point of view of vectors and matrices, the chain rule is literally a statement about multiplying matrices. And in particular, notice we get the same pithy little rolls off the tongue summary: differentiation turns compositions into products. Okay. All right. Real quick, let me point out that while I drew the picture for 2 dimensions. There were 2 x variables, 2 y variables, 2 z variables. Notice how that has nothing to do with the argument. That was just kind of an arbitrary choice that I just kind of happened to, I don't know, it was easier to draw, I guess, right? But if I were to make this a 3-dimensional domain, and maybe we leave this one 2-dimensional, and then this one maybe is a 3-dimensional target. Well, it doesn't really change the argument. It still remains that the derivative matrix still turns vectors into vectors, and the whole argument goes through exactly the same. The dimensions don't matter. This works, in other words, for any dimensions of functions. Okay, and with that in mind, let's look at this next example. Bunch of givens, and we are charged with the task of computing the derivative of the composition. Okay. Everybody good? Okay, well, and we also want to compute a certain partial derivative. We'll get to that in a second. First, let's talk about the derivative matrix of the composition. Here's our chain rule that we just wrote down. That's just copying straight out of the previous page here, right? Derivative of a composition, product of the derivatives. Oh, do be careful to notice in the composition here, the function on the left of the composition is the one whose matrix is on the left in the product. The one on the right in the composition is the one on the right in the product. So again, copying that down, notice I did the same here. It happens to be that they're still G and F, right? Alphabetic convenience, coincidence, doesn't really mean anything. But the one on the left is the one on the left, the one on the right is the one on the right. Okay, so if I want to compute this matrix on the left, I'm going to need to figure out what these matrices are in the product on the right, and then I'm going to have to multiply them. So where are we going to find these matrices? Where is, for example, the derivative of f evaluated at the point 1, 2? Oh my gosh, look at that. It's right there. It was given to me. Sweet. So that's just a recopy job. Is that cool? Next, I need to know where is going to be the derivative of g, but evaluated at the point f of 1, 2. Okay, well, here's a derivative of g, but this derivative of g is evaluated at the point 3, 1, 0. Is that okay? I mean, can I just kind of plug in dg evaluated sort of anywhere? No, of course not. I need specifically dg at the point 3, 1, 0. Lucky break, these are the same points. Again, as given over here, f of 1, 2 is 3, 1, 0. Yeah? Okay, I do want to point out there's a tricky bit to this. You do have to be really careful. When you use the chain rule, there is an aspect of this that is fundamentally different from single variable. In the single variable chain rule, you write this down, for example. It doesn't matter which order you write these derivatives. They're numbers. Number times number doesn't matter which order you multiply them in, right? Sadly, the multivariable chain rule is not a statement about products of numbers. It's a statement about products of matrices, and matrices do not commute. So the order really does matter. And here's why I say this is tricky. Because even though it kind of works out like you would expect, at least from the point of view of the order of the composition and the order of the matrices down here, G on the left, F on the right, G on the left, F on the right, it's just exactly what you would hope. It's sort of the opposite of what's indicated in the diagram. And it's not my fault. I can't change this. This is not a matter of policy. This is just is, right? This is ultimately, I blame notation, but this is all extremely standard, and there's just really nothing you can do about it. So just to emphasize, F here, the first function to act is on the left, even though its derivative matrix, and if you think about how matrices act on vectors, also still the first one to act, right? If you multiply this product by a vector, df acts on that vector still first, right? It's just that now first is on the right. And second is on the left. Here, I want to do this with numbers. Let's see here. Let's do it like this. So that is first in the diagram. That just happens to be on the left. This matrix is first in the matrix product. Happens to be on the right. The second function, G, is on the right in the diagram, and second is on the left in the product. So that's a tricky little, nasty little landmine that's very easy to step on. And you got to be really, really thoughtful and careful about making sure you get your matrices in the correct order. If you switch them, catastrophic failure. Right? It's a huge problem. Okay. Now, I want to share a personal story just because I think it's useful for helping students to remember this issue, and that is that I actually stepped on this landmine. When I was in graduate school, it wasn't this exactly. It wasn't matrices and chain rule and stuff, but it was something that's structurally kind of the same deal, where the diagram goes in one order, but the notation makes it go in the other order. And you have to keep in mind that when you're a graduate student and you're working on a hard problem is not something that takes you an hour to compute. A hard problem is something that takes you several months to work out, right? So I was in the middle of a hard problem, and I made a mistake of morally this sort, right? And I didn't discover it for a month. And I had to take a month's worth of work that had followed that mistake that I made. This was one little stupid little mistake, right? I had to take a month's worth of work and throw it in the trash can because it was all wrong. It was all based on a flawed calculation in which I had made, again, morally this mistake. Right? So, as I like to say it, I don't make that mistake anymore. I have learned extremely well through the School of Hard Knocks. Heads up, be really careful, because if you get it backwards, you're not gonna like it, right? So I'm hoping that from that story, y'all can learn from my School of Hard Knocks education, right, and not make the mistake yourself, and save yourself that pain. Okay, all right. So, along those lines, what made this question a little bit tricky? For students who weren't thinking carefully about what's the order of things and what's first and what does first mean in the in the diagram versus the algebra of matrices versus compositions. If you're not thinking carefully about this, notice the DF matrix. I gave it to students on the left, even though in the actual algebra, it needs to be on the right. And the one that I gave to you on the right needs to go over onto the left. Right? So that again was deliberate. I want to check and make sure that students are paying attention to this kind of thing, because this is an important issue. The order that you write the things down, very important. So be on the lookout for this kind of, this test of who's paying attention. Yes?
Sorry, so it depends on the formula, like if G always comes before F, or does it depend on the matrices?
It depends on what you've been asked to compute. Now here I've been asked to compute the composition G compose F. And you have to remember, when you look at a composition like this, which one of these two functions is acting first? And it's F. It's the one on the right, because that's how function notation works, right? I mean, whether it should or shouldn't, strong case can be made that it shouldn't. But that's just a reality, that the one that's on the right is what acts first. And so that's why it's on the right in the chain rule there as well.
So if we were asked F composition of G,
If you were asked F composition of G, then we go the other way.
Oh.
That's right. Yep. Okay. All right, enough of that. Okay, so, but yeah, we've got these matrices. We multiply them out, arithmetic. Y'all can do that, and here's our answer, and game over for the first part of the problem. This derivative matrix is that right there. Now let's look at the second question. The second question says, what is this specific partial derivative? So let's think about, okay, what is that a partial of? Partial of what with respect to what? Well, it's a partial of Z3, which you'll see is right here, which is the third output variable. Okay, well, keep in mind that when you're looking at a derivative matrix, outputs correspond to rows. So the fact that we are looking in the at the third output variable means that we're interested in the partial derivative in the third row down there. And then likewise, notice we're taking a partial with respect to x1. x1 is the first input variable for my composition. Remember, input variables correspond to columns. That means that because we're looking at the first input variable, we need the number in the first column. And so all of this together, we are interested in the partial derivative in the first column, third row, and that is that number 3. See? Yeah. Mm-hmm.
So is that entire matrix kind of just supposed to represent like what would just be dz dx?
I mean, I hear where you're coming from. Yeah, we don't say it like that because it's just not. Yeah, but I know where you're coming from. Yeah, this is the matrix that is the partials of all of the z variables with respect to all of the x variables. Yeah, totally. Yeah. Okay. All right. Okay. Moving along. A couple of special cases. There's nothing particularly deep about these special cases, so I'm going to go through this a little on the quick side. In this first special case, let's see, let me enlarge. There we go. In this first special case, I'm composing two functions. What's special about it is, you may notice, there's only one input variable in this composition. So that changes, and that has certain consequences about the shapes of the various derivative matrices. Right? It also has consequences in terms of how you visualize the function. So in particular, if you look at the x function here, that x function is not just variables as functions of other variables. Now it's arguably position as a function of time. It's a parametric curve. And being as there's only one input variable, when I write down the derivative matrix, there's only going to be one column. And so this, the derivative matrix of the first function, is just the velocity of that parametric curve. So nice little observation about how you can think about that. Now let me further observe the composition here. The composition gives various y variable, coordinates, again as functions of t. Position is a function of time. Position in a different world, right? Position in Rm instead of Rn, but it's still position is a function of time. It's a parametric curve. And this is the derivative matrix of that parametric curve. Again, only one column because there's only one input variable to the composition. Everybody on board so far? So you can think of this as kind of a statement about input parametric curves and output parametric curves as pertains to this function, right? So what I really have here, looking at this function f, the points that go into f are points on the green parametric curve. Those points on the green parametric curve then go into F, and out come the image points on the blue parametric curve. And what the chain rule is saying then is that the derivative of the F function is relating the velocity of the input parametric curve to the velocity of the output parametric curve. In fact, what this is saying is something we already knew, that derivative matrices relate input velocities to output velocities. So again, we already knew that. This is just kind of a different take on it, so you can view this fact as a kind of a point of view on the chain rule, this special case of the chain rule. Or, as I presented it earlier this week, you can view this statement about derivative matrices, relating input velocities to output velocities, just as a fundamental property of derivative matrices. That's what derivative matrices do. So, kind of a familiar interpretation. And here is a quick example of that. I'm going to leave the details out, but if you look at what we have here, we have a function with a domain and a target, and I have basically an input velocity and an output velocity. My input velocity is here, right? There it is. There's the velocity vector 4, 3. That represents my input velocity, and I've been requested to compute the output velocity. Right, so how am I going to compute this output velocity? Well, the derivative matrix does it for us. The derivative matrix, now some algebra goes into the computation of the derivative matrix, but the derivative matrix is the thing that you multiply by your input velocity to get the output velocity that you've been asked to find. What do you think? Everybody follow that? Okay. Real quick, special case of a special case. Here, not only do we have a single input, just like before, so I can view this as kind of two parametric curves, and F is like a relationship between two parametric curves. Fine. Here, also, only one output velocity, output variable. Again, you see it right there. It's just y. So now, two things are interesting. First of all, the product. Let's see here. The derivative that we're looking for. Right, the derivative of the composition is a Calc 1 derivative. One variable in, one variable out. Just how fast does a quantity change? It's a real familiar concept. Right? The other thing that's interesting is that you can interpret this matrix vector product. If you look at it and think, how do I multiply this matrix times this vector? Well, again, it's kind of an old news kind of a thing. Multiplying this times that, there's only one row, there's only one column. You compute this by dot product. Right? It's literally a dot product. And furthermore, this row that I have here, this is all of the partial derivatives of this one coordinate function y, of which there's it's just a single coordinate. It's not a vector, right? So this derivative matrix is effectively a gradient vector. And so I can interpret this instead of matrix times vector, I can view this as gradient dot vector. And that's just kind of a sort of notational alternative. Okay, and I'm sure I'm out of time by now. Okay, we'll call it there. Y'all have a good weekend. See you on Monday.